Okay, so hello everyone, can you hear me? Great. So I'm sorry, I'm still overseas, so I'm not in Adelaide, so we have to do this session online. So this will be a Zoom only session. So well, basically today, well, my internet might be my connection might be not stable, so I will turn off my video. Okay, cool. So today, actually, we are going to talk about a research topic, actually, uh, well, which basically this topic is very famous one, which is called image captioning and visual question answering. So uh, I'm working on this research topic since 2015, and this one is one of the uh, best research topic in Adelaide. So, well, there are four parts in my today's lecture. At first, I will give you a very brief introduction about the task of vision and language, and then I will introduce the May-Chand model of image captioning and visual question answering. That's basically the CNN and RNN model. I will also show you some of our recent works in both of these two areas. And our proposed method basically produce state-of-the-art performance and lead to many new features. And finally, I will conclude by giving some important messages. Okay, so uh, computer vision and natural language processing are basically two independent research areas. So computer vision is a field that includes methods for acquiring, processing, analyzing, and understanding images, right? The main tasks of computer vision include image classification, object detection, segmentation, and so on, right? So you already know many image classification tasks. And if you have learned the computer vision course, you actually know what are they, right? So basically for the image for the image classification, we want to classify the image into different categories. Just like the first technical session, we introduced the CIFAR 10 and CIFAR 100 image dataset, and we want to train a linear classifier and SVM to classify them into different categories. And we also introduced the convolutional neural networks, how the convolutional neural networks can classify images into different categories. And we also have the object detection task. In that task, we want to detect, we want to give an object bounding box of the interesting region. And another side is called natural language processing, right? Natural language processing, NLP, is a field of artificial intelligence concerned with the interactions between computers and human natural languages. So NLP covers a wide range of research topics such as language generation, understanding, parsing, and sentiment analysis. So I know some of you proposed a project about the sentiment analysis, right? You have the data from the review of the IMDb, and you want to classify those positive and negative categories. This task is also called as a sentiment analysis. So we also have the task of machine translation, which is actually one of the most important tasks in the NLP, right? So we input Chinese and we want to output the English, right? So, and we also have the problem of question and answering. And actually, well, both of the computer vision and natural language processing requires technique of machine learning, pattern recognition, and both of them are benefit from the recent development of neural networks. So many of the state of art in these two areas are developed based on the neural networks, right? So that's why we want to combine the vision and the language actually. So however, the interaction between the language and the vision is still largely unexplored. So we called it as a vision and language problem. So this is a particularly relevant topic to the vision community because humans routinely perform tasks which involve both modalities. Furthermore, actually integrating language with vision brings the possibility of expanding the horizons and the tasks of the vision community. For example, if we combine the computer vision task, like image understanding is one typical task in vision. So if we combine the image understanding with language generation in the NLP, we have a new task in the vision language called image captioning. So in the image captioning, the input image, but we need to understand that, sorry, we need to understand that image and then turn that image into a sentence, right? It's called image captioning task. It's kind of a new task. It requires a machine, of course, to understand the image and has ability to generate a new language. And if we combine the several computer vision tasks like image classification, detection, segmentation, object counting, color analysis, and the question answering in the NLP. So in the question answering in NLP, it's like we have a question and we want a machine to automatically answer that question. Right? So if we combine the computer vision multiple computer vision tasks and the NLP question answering task, we have a new task called visual question answering. In the visual question answering, the input is the image and then question, and we want the machine can understand that image and answer that question, right? So for example, here, what color is the tablecloth? And the answer is white, right? So we want the machine has the ability to understand the image as well as the question, then to answer that question. Now let's start with the image captioning, right? Because today I want to introduce the image captioning and the visual question answering. They are two very interesting topics. So firstly, about the image captioning. So the definition of the image captioning is quite straightforward. So it's automatic describe an image with natural language. This is a quite challenging task because it requires a machine not only understand what is happening inside the image, but also has the ability to generate human readable natural languages, right? So here shows some quite impressive example of automatic image captioning. Some details are predicted very accurate. For example, this one, man in black shirt is playing guitar, right? So we know that the black, which is the color of the shirt, and the girl in pink dress is jumping in air, pink. So we can know the colors. There are a lot of details can be described by using natural language, and our machine can understand that image very well. So this is called the image captioning. That's a task. Okay, so people actually started to study this problem several years ago, even before the popular deep neural networks. Some early methods posed the task as a retrieval problem, so where the most compatible annotation in the training set is transferred to a testing image. So what's that mean? So basically that means give me a new image, right? Just to try to search the best matched image in the training set that is similar to this testing image. Then I just use the description of that training image and the description of this testing image. So there is actually no language generation process. So it's not interesting anyway. So some previous methods are also based on like filling a template. That means some keywords are detected in the image at first, and then these words are filled into the previewed template to construct the description. There is no novel sentence generation process either. Well, in contrast to the aforementioned method, the recent main trend in the image captioning is actually to use an architecture which connects a CNN to an RNN, a convolutional neural network, to a recurrent neural network to learn the mapping from images to the sentences directly. There are lots of papers have been published in the top tier conferences using this pipeline since actually 2015. Okay, now let's see how the framework looks like, right? How so we talk about CNN, RNN, right? How that CNN, RNN works. So the framework can be considered as two parts, the CNN part and the RNN part. So basically, giving an input image, a pre-trained CNN is first applied to extract the image features, right? We know that CNN can use to extract the image features, right? So basically, we use a pre-trained CNN to extract the image features, and then these CNN features are fed in the recurrent neural network to generate word sequences, making a human readable sentence. These two networks can be connected as a whole network and trained end to end. So in the following lecture, I will introduce these two parts separately. Okay, at first, the convolutional neural networks, right, CNN. So I think most of you have heard about this word more than 1,000 times since you start to work on the computer vision and machine learning, right, convolutional neural networks, and we have introduced this one in our last technical session. So a convolutional neural network is a type of feed-forward artificial neural network in which the connectivity pattern between each neurons is inspired by the organization of the animal visual context. So a convolutional neural network is made up of layers, and every layer transforms one volume of activations to another through a differentiable function. There are three main types of layers to build the CNN architecture, right? We introduced that in the last technical session, which are convolutional layers, pooling layer, and fully connected layer. And the first successful applications of CNN were developed by LeCun in 1998. This architecture is known as LeNet, which was used to read zip codes, digits, and so on. So that's a CNN part, right? So VGGNet are widely used to extract the image feature. So there are so many, maybe hundreds of different architectures of the convolutional neural networks, but we know that the architecture is made up by convolutional layers, pooling layers, fully connected layers, and so on, right? So, but VGGNet is just one of them, but VGGNet actually is widely used to extract the image features, mainly because it's high performance and it's also available in many open source software. So a VGGNet includes convolutional layers, pooling layers, and three fully connected layers. So most of the image captioning works use the second fully connected layer. So we have three fully connected layers. We call it FC, right? Three FC layers. But actually, most of the image captioning work use the second fully connected, use this layer to extract the image features, which is actually 4096 dimensional. So why do we want to use this? Why we choose to use the second FC layer output to represent the image, and what do the neurons learn? So Ziller et al. Actually visualize the features of each layer in the CNN, and it shows that the lower parts of the layer, for example, the lower part of the convolutional layer, respond to the corners and other edge color conjunctions. And in the middle layer, have more complex invariance, capturing similar textures such as mesh patterns, while the higher layer actually are more class specific, such as birds' legs, dog faces, and so on. So a higher layer, like the fully connected layer, can capture some high level information in the image, right? So basically, the higher layer can capture more semantic information, like the parts of the car, those kind of things. So of course, if we want to generate high level image descriptions, we want to use the higher layers of the features. Well, summary so far. So we can say that convolutional neural networks express a single differentiable function from raw image pixel values to the class probabilities, and the fully connected layers can be used to extract high-level image features. Right? That's the CNN part. So we will not spend a lot of time on the CNN part because we have introduced it several times. So then we go to the next step, the RNN part, the recurrent neural network language modeling part. So as we mentioned, so we have a CNN-RNN architecture, right? CNN part is used to extract the image features, and we use the RNN part, the recurrent neural network part, to model the language generation process. So before we talk, talking about more details about the image, about the RNN, so let's talk about some applications about it. So RNN are good at modeling sequences. For example, generating handwriting for a given text, which is known as handwriting synthesis, right? So we can generate some handwriting examples by giving some real examples, right? So it's called handwriting synthesis. So it even can generate Wikipedia data by giving a large number of training examples. So if we can train, for example, if we can train on all the Wikipedia data or news, right? So we can actually automatically generate the news or Wikipedia page by using the recurrent neural networks because it's good at modeling the sequence. So it also can predict the word given the previous seen word sequences. For example, when we type some word in the Google search engine, right? So you type some word, but sometimes it will give you some suggestions like they will fulfill that sentence, right? So when we type some words in the Google search engine, some predicted words will be appeared to complete that sentence, right? So for example, here, if we in the Google we just type cat sat on these 4 words, then the Google search engine actually can automatically predict what kind of things we want to search, like cat sat on the mat, cat sat on a barrel, this kind of things. So this RNN can use to help us to complete sentence automatically. So it also can be used in the machine translation. For example, giving a sequence of French words, RNN actually can predict the English word sequence as a output. So in the Google translation, so previously, I mean, like 10 years ago, the Google machine translation used the maybe template-based method. But now then like 2 or 3 years ago, they were using the recurrent neural network, more precisely the LSTM, non-short-term memory machine, to do the translation. And now they are using transformer, right? So, but the recurrent neural network is one of the best model to do the machine translation. So, then let's go to more details. We know that recurrent neural network is very useful. Now let's go to more details about what is a recurrent neural network unit, what is RNN, right? So basically, a recurrent neural network is a class of artificial neural network where the connections between units form a directed circle, right? So this actually creates an internal state of the network, which allows it to exhibit dynamic temporal behavior. So unlike the feed-forward neural networks, RNNs can use their internal memory to process arbitrary sequences of inputs. So the internal memory or state can be updated while this formulation. So basically where the HT is a current new state, and FW is some function with parameters W. And HT minus 1 is the old state from the previous time step. and xt is the input vector at the current step. So basically, you can think the recurrent neural network as a chain. So the input of the each RNN unit is all the state and an input vector, but the output is a new state, right? It's like a state machine. By using the RNN unit, you can use the previous state and the current input vector to predict the next state, and the next state then can be translated to a new word, right? So, and we should notice that the same function and the same set of parameters are used at every time step. So there are actually several variants of the RNN, such as LSTM, non-short-term memory machine, the BLSTM, GRU, and so on. So here we take the vanilla RNN as an example. The state only consists of a single hidden vector, hidden vector H, and the H is calculated by a hyperbolic tangent function, so tangent H. So basically, that means that an FW is basically just a linear function and a nonlinear function. It's just a simple neural network, right? So because HT here, so basically HT minus 1 is the previous state, XT is the current input vector. So this is a linear combination, and tangent H is a nonlinear operation. So this is the simplest, we call it the vanilla RNN. So then we can have the new state, which is HT. Then with this HT, we can do a linear transformation and to predict something we want to predict. Right? So that's vanilla recurrent neural network. So how it works in the language modeling, right? So it's the concept of the RNN of the recurrent neural network is quite simple and straightforward. It just give me a previous state and give me a input vector, and the output is just the next state, and based on next state I can predict the next output, right? So that's the basic idea of the RNN. So how it works in the language modeling, because we know the language modeling is a sequence problem, right? Sequential problem. So here, suppose we have the training example cat set on mat, and we want to train a language model to maximize the probability of generating a correct next word given the previous words, right? That means we want to this the functions to be high, right? So that means pcat giving the start token, pset giving start token and cat, on give the set and cat, right? So that means give me a start token, I want to predict cat, and give me a cat, first word of cat, I want to predict the next word as set, right? Give me a set, cat set, I want to predict the next word as on, right? So basically, if we want to maximize this probability, given the previous word, predict the next word, if I want to maximize this, I want this probabilities to be high. And RNN actually provides us a sequential way to model this process. Okay, so this page actually shows the modeling process. So at the start of the modeling start token here x0 will be input to the RNN unit to produce a hidden state of h0. Then this hidden state h0 produces the output y0. And then if we apply a softmax function on the y0, it gave us a prediction of the next word. Can be written as the p word given the start token s. This process will run sequentially until the last word, the mat, is inputted, and our task is to output to update the parameter in this network to maximize the summarize of all these probabilities given the ground truth, right? So remember in last page we say we want this probability to be high, and in RNN actually we can for each output, this actually gave us this output, gave us this probabilities, right? Because we actually at each time step we input the previous time step. That means it's based on the condition of a previous word, and we also input the current word, and we want to predict the next word. We want this probabilities to be high. So there are, of course, in this whole process, there are several parameters need to be learned. At first, at the input side, the input word first needs to be encoded as a fixed length vector. This normally can be done by the word-to-vector model, but in some cases, we found simply formulate the word as a one-hot vector is also fine. But we will need to preview the vocabulary in that case. Then the WXH over here is the embedding weight, which embeds the input words vector to the RNA unit. And WHH here, the WHH, which is for the hidden state, is the hidden state weight. And the current time step hidden state is calculated by the input vector and the embedding vector hidden state weight and the previous hidden state, right? So basically this is the vanilla RNN, right? So the new state will equal to the previous state and the current input vector to summarize them, right? We also need a nonlinear operation. Okay, so and at the output side, we also need the decoding weight that can decode the RNN output vector to basically decode the hidden vector to a probability distribution upon the output words vocabulary. Say, for example, if there are 10,000 words, then we need 10,001 words in vocabulary, one for a special end token, right? Because sometimes we need to know, well, this is end token of the sentence, right? The end of the sentence. So we need to predict that word, the end token correctly. So the whole network can be trained on a lot of given sentences and optimized by the SGD, which is a classical optimizer. So after this model is trained, we got a way to predict the next word given the previous word, right? So that's how the RNN works in the language modeling. So after introducing and discussing the CNN and RNN part separately, we basically connect these two parts as a whole to see how it generates descriptions giving an image, right? So we introduce the CNN to extract the features, and we introduce RNN to model the language part, right? Then how can we combine them together to generate the descriptions, language descriptions for this image? So, so let's say this image captioning training process. So here we take this training pair as an example. For example, inside this one, the image is a man wearing a straw hat, and the text description of this part is just a straw hat. Of course, normally the sentence is should be long, like an old man is wearing a straw hat, something. So here for simplicity, we just use two words to describe this image. It's called straw hat, right? So this is a training example. And because we are using a CNN model, right? So at first, the image will be passed to the CNN part. As we mentioned, that will be passed to the CNN part to extract the image features. And as we discussed before, we will use the second fully connected layer, this one as the image feature vector, as the image features. Then the image feature vector will be multiplied by a learnable weight and used as initial hidden vector for the RNN unit. So before, actually, you remember in the pure language modeling part, when we don't have image, the H there, so before this one, so if we don't have the image, so H initial actually equal to 0, right? So we have nothing to input because we don't have the image. And but now, because we use WRH to multiply the image features V as the initial hidden state, So in this way, the image, so here that's a new function. So we actually plus WIH times V and input to this hyperbolic tangent function and to calculate the new state H0, right? So in this way, the image features are are passed to image information is passed to the RNN memory and will affect the description generation process. Actually, there are several ways to deal with the image features. You can use as the initial hidden state, as we showed here. We can also actually use it to replace the start token X0 as the initial input. The work from Google did it in this way. So we also can input the image features with word features together at each time step. Some paper from Baidu did it like this. But the final experiments show that there are no big differences actually. So the further language model training part is the same as we described in the previous language model process. So that's the training process of the image captioning model. Now in the testing, right? So in the testing, well, let's assume we have we have a test image. Right? So here is actually the same image. The test image will be first passed to the CNN to extract features, and the image feature will be used as a initial hidden state. Then input the start token to the first time step RNN unit, and output will be generated by this RNN unit. In this case, it's a probability distribution of the word's vocabulary. And if our model is trained well, in this case, the first word straw will be has the biggest probability. Then we use output or Y1 straw as Y0 straw actually as the input of the next time step. It will be give us a next word prediction. Y1 will, for example, it's a hat. Then we input this output to the next step input. Then it knows that, well, I have finished generating word sequences, and it will give us an end token. That means I'm done, right? So that's the testing process. So that's the image captioning generation process. Basically, give an image, use the CNN to extract features, send the features to the trained language model. Then the language model will predict word by word. And at each time step, the predicted word will be used as the input of the next time step, right? So in this generation process, we also can search longer phrases with beam search, which is just a kind of simple searching strategy that we'll not introduce here. Okay, so basically, the performance can be further improved by replacing the vanilla RNN by the LSTM, right? So the LSTM is called the long short-term memory. So LSTM is basically an RNN cell which changes the form of an equation for H, such that at first more expressive multiplicative interactions, and secondly gradients flow nicer, and last the network can explicitly decide to reset the hidden state. So we can avoid the gradient exploration and gradient vanish issues. So basically, this is the vanilla RNN, as we mentioned, the function in this unit is quite simple. It's basically just a neural network, a simple one-layer neural network. But this is an illustration of the LSTM cell, and the formulation of the hidden state computation, as you can see, is very complex, right? It has something called input gate, get gate, output gate, and the memory cell, right? It's much more complex to process memories inside the LSTM, much complex than the previous vanilla RNN. So of course, it has more parameters, but it can avoid the parameter vanishing problem. which is a serious issue for the recurrent neural networks. So the LSTM is widely used in the image captioning and other language generation model. So, well, we have reviewed both of the CNN and RNN part of the image captioning models in the previous pages. So in the next few slides, I will discuss the value of high-level concepts in the image captioning. All right, so the CNN plus RNN model enable us to learn mapping from image to sentences directly. This is actually attractive, right? So remember the CNN RNN network. Input this image into CNN and directly use RNN to generate a sentence. So basically, we are learning a matching from the image to sentence directly. However, for our, human beings, when we want to describe an image, we may want to first to observe the visual concepts in the image, and then use this visual concepts to make a sentence. So a good question is to ask whether there are something missing between the image and the sentence, right? So if we want to answer this question now, let's go back to the page of what do the CNN neurons learn. So because we used the higher layer of the higher level of the layer to extract the features. So let's focus on the higher layer. Looks like the features we have learned are most objects and object parts. The more importantly, these features are implicitly represented, right? They are just the features. We after we visualize them, we may know what are they, but they are just implicitly represented. They are just the numbers, right? So what we really want to use to construct the sentence are those high-level visual concepts represented implicitly. So for example, in this image, if we can detect the visual concepts such as group, dinner, party, and even the word of happy, and some other objects and actions, we may have a bigger chance to generate better image descriptions. So this is a motivation of using explicit visual concepts as a bridge between vision and the language, right? So based on this, so technically, based on the classical CNN framework, we simply add a visual concepts prediction layer, which is shown in this blue box. Basically, in some sense, we add a word layer to bridge the gap between the image and the sentence, making it act more like humans. So the framework is very easy. So give me a CNN, give me an image. Instead of using CNN to extract features directly, I send it into a multi-label prediction CNN and use it to predict the words. We call it visual words or visual concepts. Like we can predict, okay, there is a pizza, there are some people, and they looks very happy. Right? We predict a lot of attributes, visual concepts. Then we input those concepts into the sentence, into the LSTM model to generate the sentence, right? So basically, we build a bridge to gap the image and the sentence. We add a words layer between the image and the sentence. So this work actually was done by me in CVPR in 2016, and we got that that paper has been accepted by the CVPR. So we formulated the visual concepts prediction as a multi-label classification problem. I remember we input the image, but we want to predict the sentences. We want to predict the labels, the multiple labels. So to solve the problem that some visual attributes only appeared in some regions, we apply a region-based multi-label classification framework to predict image labels. The model is first initialized from the VGGNet pre-trained on the ImageNet. Secondly, the model is then fine-tuned on the target multi-label dataset. So given a test image, a set of proposal regions are selected and passed to the shared CNN to produce the final multi-label prediction. the prediction score of these labels actually will be fed into the LSTM to generate the sentence. So we evaluate our model on the Microsoft Cocoa image captioning challenge. Our model was ranked first place according to the, so we also need to evaluate the caption, right? So that means we need some evaluation metric. There are several different types of evaluation metric, like BLEU score or BLEU score. From B1, B2, B3, B4, and mental and CIDR score. These are all evaluation score. Basically, higher is better. And then we can see our method performance much better than the previous data developed by the Google or Microsoft research. So this figure actually shows some qualitative results of our image captioning models. So for example, for this image, two bears are fighting, right? So we can first predict some attributes or visual concepts appeared in this image, like brown, small, laying, playing, grass, is two bear. So we can predict these words and give them some probability. Then we input these scores to the LSTM to generate the sentence. So here our the black sentence is the result generated by our model, like two brown bears playing on top of a lush green field, and the blue sentence is the baseline results. It's basically a CNRN model. A bear is walking through a grassy field, so it's actually not quite right. And the red one is a ground truth. It's a sentence given by a human. So two brown bears playing in a field together. And as you can see, actually in this example, our sentence is even better than the human generated ones, because we can predict like a lush green field, right? But in the human annotated sentence, it's just in a field together, right? So we can predict the more accurate attributes. That is because our multi-label prediction system. Okay, so now let's head to the, so we just introduced the image captioning, right, which is one of the earliest and actually hottest topic in the vision and language. Now let's head to the another interesting topic, which is called the visual question answering. So visual question answering is a much more challenging task than the captioning. So basically in this vision to language problem, an image and the free form, open-ended questioning about the image are presented to the method, which is required to produce a suitable answer. So for example, here, give me this image, right? So what color are her eyes? And we want the machine to understand this image to find out the eyes of this woman and try do the color analysis and give me an answer, like for example, black, right? And what is mustache made of? Of course, banana. And we also want to know the numbers, like how many slices of pizzas are there? Is this a vegetarian pizza? So the model need to analyze whether there are any meat on the pizza. Right. So does it appears to be raining? We need to check the weather. Does this person have 20/20 vision? Of course not, because he wears glass, right? So we need to have common sense knowledge to answer questions. So that's the task of the question answering, which is much more challenging than the image captioning. In the image captioning, give me an image, I just need to generate a language description. But in the VQA, the visual question answering, we need to answer that question. And to answer that question, we need a lot of different knowledge. The knowledge from the image, we need to know the object, attributes, colors, size, numbers, and we also have to have the common sense knowledge, right? So that's why this VQA problem is a very challenging one. So like the image captioning, there are also a lot of works based on the CNRN framework, including our visual concepts-based method. And we also developed the two methods based on the knowledge base, which will be introduced later. So some methods are based on visual attention. They encode the visual attention model into the visual question answering process. So I will introduce the visual attention model later as well. Okay, so the CNN framework for the VQA is actually very similar to the image captioning. So basically, we can use the CNN to extract image features and use RNN, the recurrent neural network, to generate answer. Except that we need input the clustering to the LSTM as well. It is shown in this blue box, right? So as you can see, this is a typical CNN framework. So in the image captioning, we input the CNN into the we input the image into CNN to extract features, then use a recurrent neural network to generate a sentence. But in the VQA, because we also have a clustering, and clustering is also a sequence of words. So that means we can actually input the clustering into the LSTM, right? Into the LSTM as well, and combine the features together to give us an answer. So this is a CNN framework for the VQA. And similar to the image captioning, we can also add the words prediction, the visual concepts prediction layer between the CNN part and the RNN part. So basically, instead of using the CNN features directly, we first predict the visual attributes from this image and input these attributes into the RNN part to understand the question and combine with the question feature to answer that question. So that means VQA can be also served by using the CNN framework and as well as word prediction. However, in some cases, to answer a visual question, only visual information is not enough. For example, in this image, the question is, why do they have umbrellas, right? So it's these people on a beach and there are some umbrellas, right? So my question is, why do they have umbrellas? So to answer this question, one not only needs to know that the umbrella is used in sunny day in this image, but also needs to have the knowledge that umbrellas are used as points of shade on a sunny beach, right? So that means common sense are required for answering such questions, right? So we need to know those external knowledge like an umbrella is a canopy designed to protect against the rain or sunlight. Larger umbrellas are often used as a point of shade on a sunny beach, and the beach is blah blah blah. We need to know this common sense knowledge to help us to answer the question, right? So there are two more examples. For example, here, the question is how many mammals in this image, right? From this image, we can see there are 3 animals, dog, cat, and the bird. If the question is how many dogs is here or how many animals are here, the answer should be easy, right? But our question is how many mammals in this image. In that case, we need to know that dog and cat are mammals, but bird is not. So the answer of the question is 2. Right? We human can answer this question easily because we know dog and cat is mammal, but bird is not. But the machine has no knowledge about whether bird is a mammal or not. It has to go to a Wikipedia or go to some external knowledge source to find out the answer. And see this image, why are they wearing such bright color? So the yellow, orange, why are these people wearing such bright color? Of course, for the safety reasons, we know that, right? We know in Apple this for safety reasons. We know bright color can be used for safety reasons, but machine doesn't know that. We need to give this kind of knowledge to the machine so that the machine can answer those questions. So, okay, so next part I introduce how can we relate the knowledge base to the VQA, right? How can we use the knowledge base to help us to answer those knowledge-based related questions? Okay, so let me check the time. Okay, it's 2 o'clock, so let's have a break and let's come back 10 past 2. Okay. Okay, so welcome back. So let's continue. Right. So yeah, we talk about the visual question answering problem, and we know that there are many examples in the Wikipedia that we need to use the common sense knowledge to answer, right? So then a natural question is to ask, how can we connect those common sense knowledge into the visual question answering? So yeah, okay, yeah. So a knowledge base, right? So a knowledge base known as a KB is a technology used to store the complex, structured, and unstructured information used by the computer system. So Wikipedia, the Wikipedia page is actually a kind of a knowledge base. But of course, all the information are stored unstructured, right? Unstructured, right? Because they are just paragraphs, text, images, right? So they are unstructured knowledge base, but it's a kind of knowledge base. But there are also many structured knowledge base like DBpedia, Freebase, ConceptNet, WebChild, and so on. So for the DBpedia is actually the structured version of the Wikipedia. So most of the information in the knowledge base is stored as a triplet, which represented as entity one, relationship, and entity two. This makes some standard query language can be used to search the knowledge. Some example common sense knowledge such as dog is mammal, cat eat fish, bike is cheaper than car, right? So this kind of knowledge are stored in DBpedia ConceptNet. So then if we can check dog, if we want to know whether dog is mammal, we can check dog's entity and check mammal, and the answer is yes. So that means yes, right? So we can check the common sense knowledge by using some query language. So knowledge base can provide unstructured knowledge as well. For example, here, so this is a paragraph from the Wikipedia actually. So it's a textual explanation of a concept. Here we show an example from DBpedia, which is describing a dog. The domestic dog is a furry, carnivorous member of a Canadian family, mammal class, right? So it's unstructured, it's just a pure natural language. But we can use this query language to query the dog in the DBpedia, right? And then we can actually use this mine the text this are common sense knowledge. We can use the information to help us to answer those questions, right? What we need to do is to encode this text into some feature vector, right? For example, we can use a word2vector, a documents2vector, or even just LSTM to encode this language, this sentences into a feature. Then we can actually input this feature into a model to answer that question. So based on this, actually, we proposed a method which combines both inter-image representation and the external knowledge base. So here, giving an image, a CNN is first applied to produce the attribute-based representation. This is the same as attribute multi-label classification model in our image captioning model to predict the attributes, right? So the internal representation is made up of image captions generated based on the image attributes, the hidden state of the caption LSTM after it has generated the last word in each caption is used as its vector representation. And these vectors are then aggregated with average pooling. So we basically also use our image captioning model to generate the captions of the image, and we use the hidden state of the captions as the internal representation. Of course, we also have the average pooling. Then the external knowledge is mined from the knowledge base, the DBpedia. So how can we mine? How can we get this external knowledge? So here we actually use the top 5 attributes. For example, in this image, the top 5 attributes, we have a score, right? So for example, dog, cat, bird, flower, red, those kinds of things. We choose the top 5 attributes. And we use this top 5 attributes as a keyword to search the paragraphs from the knowledge base about that concept. For example, here dog, right? A dog is what we got this knowledge. Yeah, we combine this external knowledge and send it to a doc to vector machine, so which is a documents to vector. So this is a pre-trained model that can encode all the text into a vector. Then we use this vector, we use the attributes vector, we use the caption vector, all these vectors together and send them into STM to generate to generate the answer. Right. So this part, the second part, half part is exactly the same as the normal VQA model. The difference is that here we use the external knowledge. Right. So that's how we relate to the knowledge base. So, well, here are some results. We'll not discuss them. So we also evaluate on the evaluation server. So we the best results that at that year. So this figure shows some example. I'm happy to show this one. So here, like how many people in the photo, well, we can generate the answer to. What is the red fruit? We can predict the answer apple. And the VGG-STM model sometimes predict the answer wrong. And I'm also want to show this one. Why are his hands are outstretched? Right. So this is a typical common sense knowledge question, and we can give all the answer like balance, but the VGG-STM model can only give the answer play. Right. So because we can access to the knowledge base to use those common sense knowledge to help us to answer the question. So here is a demo. Actually, you can try it. I will not try here, but you can definitely try this one. So, there are also some limitations of aforementioned CNN models. At first, we don't fully use the power of the existing computer vision algorithm, right? The only thing we benefit from the computer vision side is the extracted CNN features. And this CNN is simply trained on the object classification task of the ImageNet, right? So we only use the CNN to extract the image features or predict the attributes. But to answer visual-based questions, ideally, we should use multiple source information from the image, such as object in this image, right? So what kind of object exists in this image? And we want to know the color. So what's the color of that of those objects? We want to know the material attributes of the objects, really even the relationships between different objects and so on. So this information could be obtained from different computer vision models that have been trained on different tasks, right? So, but now we are just use a single CNN model to extract the features. Of course, this single model cannot, cover all this kind of information. And secondly, during the VQA process, no reasons can be provided. The current CNN model learns the mapping from image and questions to the answers directly. It's basically a black box, right? So we have no idea how the system concluded the answer. And sometimes the ability of providing reasons is important. For example, in the area of medical service and defense, right? So in the medical service, for example, we want to well, if one day we have a machine to replace the doctor, right? So to give we can use a machine to give a doctor some advices, right? So the patient, the doctor will ask a question to the machine. Then if the machine gives an answer, the machine must explain the answer, right? So we must have some reasons to give the answer. It's called explainable AI. But in the current CNN model, because it's kind of black model, it learns a mapping from images to the answers directly. There's no such way that can provide the reasons. So most recently, actually, we proposed a co-attention model to address these limitations. It's called the VQA machine. So we call it a VQA machine, which can benefit from multiple computer vision tasks and output the reasons as well as the answer. So as we can see in this model, we first use image, we first have an image, but different from previous method that we use CNN to extract the image features directly or predict some attributes. We first predict a lot of visual facts from the image. And these visual facts are predicted by using several different computer vision models. For example, we have the image detection model, object detection model, to predict what kind of objects exist in this image, like image contain horse. And we can also predict, we can also have the attributes prediction model to predict that this image has attributes writing. And we also use a relationship prediction model to predict the relationship between objects inside this image. For example, here, man holding rope, go on horse, man with horse, right? So we can predict like hundreds of different visual facts by using different existing on the shelf computer vision models. And we can, of course, weigh these facts. We can embed these facts into different feature vectors. But the question, all these features embedded jointly, with the images and facts, well, a co-attention model. So attention model, so the motivation of the attention model is to select the most relevant part when we processing some features. For example, for the image, for the visual question answering, if we use attention model, we can know which part of the image or which feature should be focused, should be attended, should be given more weight to answer that question. That's the idea of the attention model. So here we use a co-attention model to select which facts are important for answering the questions of this image, right? So we call it co-attention model because in the attention model, we also need to use some guidance to help the machine to attend on the important features. So here we use the question and the image to attend on the image, to attend on the facts, but also with the facts and the image to attend on the question. This is a co-attention mode. I will not explain it. It's a little complex, right? But when here, well, after we do the attention mechanism, we input all these attended features into MLP to predict the answers based on the outputs of the co-attention mode at all levels. And the reasons are generated by ranking and reformulating the weighted facts, right? Because here we use the attention model, and the attention model, as I mentioned, can give us weight of each facts. For example, maybe this facts, the weight is 0.5, which means it's very high, which means this facts has been used for answering this question. We choose the top 3 facts in this attention mechanism, and it can then translate the facts, because our facts is stored in like a triplet format. We transform it into a sentence, like the image contains object of horse, the image contains action riding, the girl is on the horse, right? So we translate those selected facts into the reasons, into a kind of evidence and how the machine can predict the answer. And this evidences, these reasons can be understood by human, right? So, and the visual facts are extracted by using multiple off-the-shelf computer vision models that have been trained on different types of tasks. So by using this model, we solve 2 problems. The first problem, we can use, well, as many as off-the-shelf computer vision models, right? If the model has the ability to predict something from the image, we can use it in the VQA. And second problem we solved in this model is we can use this, we can predict the reasons, right? Okay, so the core of our VQA machine is the co-attention mechanism. So let me explain it a little. So basically, again, means the encoded question Q and the image V and the fact features F. the proposed co-attention approach sequentially generates attention weights for each feature type using the other two as a guidance. So specifically, the initial question representation is first used to guide the facts weighting. The weighted facts and the initial question representation are then combined to guide the image weighting. Then the weighted facts and the image regions are then jointly used to guide the question attention mechanism. All that remains is to run the fact attention again, but informed by the question and the image attention weights. As this completes this circle, and means that each attention process has access to the output of all the others. So we use other two features to guide the attention of the third kind of feature and do it again and again until we find out the best attended features. Right? So that's a co-attention model. So here we show the results on the VQA data set. So compared with the method we mentioned before, so here, as you can see, the ACK is a model we proposed by using the common sense knowledge and the captioning and the attributes. The performance is 59.4. But as you can see, if we use this one, we can achieve 63.3, actually, which is a very high performance. So there are some results from our model. Well, as a colored words, actually in the question have the top 3 identified weights. As we mentioned, we use attention mechanism to select the important information from question, from image, from facts. So the highlighted parts in the image shows that this part is important to answer that question. For example, the question is what is in the water, right? So as we can see, attention model attended to the boat, the most important part of this image. And the colored word shows the top 3 identified weights. So the water, what, these are important words for answering this question. And we can also, predict the reason set to give the answer boat. We say this image contains object boat. The boat is on the water. This image happens in the scene of a harbor. So that's the reason set that why we gave this answer. And what time of the day it is, right? What time? So as you can see from the image side, most of we focused on the sky, right? So because it's blue, then that means it's a daytime, right? So here, that's the reason we gave. The sky is blue, the horse is pulling, the image contains object of road, so this kind of information. Of course, the second and third evidences are not important to answer this question, but because we choose the top 3. But if we check the top 1, the sky is blue, that's good enough for us to answer that question because blue sky means daytime, right? So that's some results we have. There are more results I will not show here. And actually, before that, I want to show some other examples. Yeah, so we call it explicit reasoning. So in our previous model, in the VQA machine model, yes, we used the attention model to solve that problem, but the reason is also given by the reasons are also predicted by using attention model, and we want to do some explicit reasoning. So what the explicit reasoning really means? So give this image as example. One asks a question that how many giraffes in this image? The answer is 2. And the reason of the answer is the 2 giraffes are detected. So if the question is that is this image related to zoology, and the answer of course is yes. The explicit reasoning process is then that giraffe to animals is related to the zoology, right? So we want to predict human understandable reasoning chain to explain how can we answer that question. So basically, we want to know how the machine concludes the answer, right? Different from the VQA machine. In VQA machine, we use the attention mechanism to select the important facts as the answer, as the reasons. But here we want to build a reasoning chain to help us to understand how the machine can understand to answer that question. So Here we designed this framework to complete the explicit reasoning process. So basically, give me an image. But first, use several deep neural network model to detect the object, attributes, scenes, and so on. Then we link these visual concepts as a scene graph and related them to the external knowledge base. So in this case, we relate them to the DBpedia. So basically, here giving a question, we then use NLP parser to pass it to multiple case to multiple RDF queries, right? And then we use RDF query to query the knowledge graph we just constructed. The query result is the answer of the question, and the query path give us the explicit reasoning process. So in this way, we can actually get the answer and the reasoning chain. For example, here, what are the common properties between the animals in this image and the zebra? It's a typical question that need to be answered by the a lot of knowledge, right? So to answer this question at the image side, we first use the CNN model to extract those objects and build a graph. And we also know the relationship between different objects. And for each object, we can connect it to the concept in the concept net or the DBpedia. This gives us a large graph about this image. And for the question, we can change it to a kind of query language. This query language can query this graph, and we can answer that question that the common properties between the animals in this image and the zebra is they are both herbivorous animals. They are both animals, and they are big animals of Africa. And this is a reasoning chain because we know there are giraffes inside this image, and the giraffe herbivorous animals, and zebra also herbivorous animals and megafauna of Africa, and the giraffe is also megafauna of Africa. So this gave us a reasoning chain. The other results I'm not sure. I can show you this one. So some visualization examples. So here we can see the question is which object in this image is most related to entertainment? There are multiple objects, windows, TV, floor, table, and so on. So we want to know which object is most related to the entertainment. Of course, the answer is TV, the television, right? But how can we get that answer? We first detect all the objects, but we know that the television is related to performing arts, and the performing arts is related to the entertainment, right? So this reasoning chain is got from the knowledge base by using our method, and we can list the common properties of the two images, right? So we know there's a train and this is a typical airport, and both of them are related to the transport infrastructure. So the answer is the transport infrastructure, right? To answer this question, we need to know the common sense knowledge that train is related to transportation, airport is also related to the transportation, and this information can be only found from the knowledge base. And we can compare images. Which image is the most related to chef? The answer is left. The answer is left one. Right? The reason is that we found the kitchen, oven, and microwave, and all these objects are related to the chef, and so the chef is related to the kitchen, right? Now, which image is most related to the programmer? Of course, the right one, because we found the computer and mouse, and we know that this kind of things are related to the programmer, right? Because we have the knowledge base, we can query the knowledge base. So that's why we need the explicit reasoning. Okay, so conclusions. So at first, so vision to language is a new and challenging task. It involves both computer vision and NLP communities. So many tasks are fall into the scope, such as image captioning, visual question answering, and zero-shot learning. So CNN model is a previous trend current trend in this field, because CNN has the ability to represent the images, and RNNs are good for sequence modeling. This framework is simple and effective. More importantly, it's end-to-end. We also find that explicit high-level concepts representation brings significant improvements in the vision to language tasks, such as the image captioning and VQA. and use knowledge base is a further direction in the VQA. Because you cannot expect the machine to answer the question only with I, but with all the knowledge. So finally, ideally, VQA should be benefit from multiple computer vision tasks. And we find that the co-attention model can be very helpful. Okay, so that's the end of today's lecture. So do you have any questions? So how to understand what end-to-end is? End-to-end means we don't need to train the model separately. We can train the model because neural networks normally have different layers, right? So we don't need to train them separately. We can train them by using the same data set and the same task. So that's the meaning of end-to-end. We don't need to train this part first and train that part secondly, right? So it's like saying, so in the CNN-RNN model, we have two parts. One part is CNN, the convolutional network, right? And the second part is the recurrent neural network. We can train them separately, right? We can train the RNN, we can train the CNN part based on the image classification task, then fix the parameters of the CNN, just plug it into the RNN. Therefore, in the image captioning task, we will not touch the CNN part, only train the RNN, right? So it's but that means we train them separately. So end-to-end means we can combine them together, train them with a single task. Okay. Each part won't influence another part. So if you train them separately, then each part won't influence another part. But if you train them end-to-end, that means this part will affect that part. This is actually better, right? So we want that this RNN part affect the CNN part, and CNN part also affect the RNN part. If we train them separately, they won't influence or affect another part. Okay, thank you. Any more questions? Okay, so no more questions. So that's the end of today's session. Thank you very much.